problem. Okay, hi everyone, welcome. So, Crunchy, you're up. So, hopefully we went okay with the first principles. I want to say a few things about it. The first thing is that this is an important skill because it pops up in about 40% of the exams. If you look in the past, it's been a continuous skill that they seem to access reasonably regularly in exams. The second thing is that there's definitely going to be in your test. There's going to be at least one, maybe two questions on first principles. So it's a skill you need to be completely competent with. First principles, here's the formula for it. And here are the ways in which I can ask it to you. Okay? Firstly, it could be a polynomial. All right, that's x to the power of n for any value of n, right? X squared, x to the power of 3, x squared take 4x, okay? That's what you did in year 11, right? You just focused on the polynomial segment of it. Where it gets more tricky at stage 2, year 12, is we look at radicals and reciprocals. So for instance, 1 on x, 3 on top of x take 2, x plus 4 on top of x take 3, and that requires cross-multiplying the denominators and so forth. Then we look at surds, okay, so square roots, and they're quite tricky because that requires multiplying by the conjugate, all right? And then you even combine surds with reciprocals, like if you have 1 on root x. Try to do first principles for that. That's a page of working, right? There's a lot of working going on there. So it's a skill we need to know and understand and not forget. There's going to be one question about it in the test. I understand some of you might not have finished the exercise yet, and I actually don't think the textbook asks enough, which is why if you look at your notes for 2A, there's lots of questions there. But then down the bottom, I've got extra problems for first principles, and there's like 9 of them there. So between now and your test, what you should be doing is one of these per each night of homework. Okay, just retain that skill and then practice it a bit further in different ways. And there are work solutions for all these questions, so you get stuck at any stage, you'll find the work solutions for it on the Google Drive. So that's what I wanted to say about first principles. Today, I'm going to get each of you to come do a problem on the back of the board so I can see your skills with it. And we're going to work on simple differentiation as well. So, let's turn the page to 2B, simple differentiation, and let's get straight into it. I'll put my examples up. I'm going to just shut this door. Alright, so let's read the table here first, and this is something you should have picked up in exercise 2A as well. We have our function. Our function of x. F of x equals y. We're going to use both of those. Alright, we're going to use f of x, we're going to use y. And if you input any x value into the function, it's going to give you the corresponding y value. It gives you a coordinate, right? When x is 5, y is going to be some number as well. But then what we learned with first principles was the derivative function, f dash of x, all right? dy on dx is the other terminology we use, dy on dx. And that's going to tell you, if you input an x value, it tells you the slope. That is, how steep is it for any value of x. So this table, very, very important. So what we're looking at today, simple differentiation. We've got a number of rules here that we're going to apply. And I've got some numbered steps to make sure you're following the rules properly. Ensure all x terms are expressed as x to the n. Function is fully expanded and at the top, okay? At the top, as in it's in the numerator. Then we can differentiate in one step, and then we can simplify if we're required to do so. So we're just going to consider the first one here. We have x to the power of 7. The first rule at the top of our page says, if you have x to the power of n, the derivative is nx to the n take 1. Nx to the n take 1. So if we have x to the power of 7, all right, so let's check. It's expressed as a single power of x. It's x to the power of n, right? It's at the top, all right? As in, it's on top of 1. It is the numerator. It's expressed at the top, and it's fully expanded. We're ready to differentiate it. Let's do it in one step. dy on dx. When you differentiate y, it goes to dy on dx. And so if we have x to the power of 7, it's going to be 7x to the power of 6. Okay? Nx to the power of 7 take 1. 7 take 1 is 6. Okay, let's move on to b. Now, we've got everything expressed at the top of the fraction. Everything is expressed as a single power of x, right? This number here, that's x to the power of 0. X to the power of 0 is 1. So that's all fine. Everything's expressed as a single power of x. We're ready to differentiate. So all in one go. dy on dx is derivative of 4, 0. When you differentiate a constant, it disappears. All right, so that's the third rule. Derivative of c, any number, when you differentiate it, 0. So you can, I'm going to write it there to start with. All right. Minus 3 is just a number. It's a product. It's going to hang out the front. And we have minus 3 times x to the power of 4. Okay, so when we differentiate x to the power of 4, that's going to be 4x to the power of 3. Alright, so minus 3 is the product. That's what we're multiplying it by. X to the power of 4, when we differentiate it, 4x to the power of 3. And then the second rule in our table there, kx, the derivative of kx is k, so the derivative of positive 6x is going to be positive 6. Okay? And so we can write it like that, and it's completely correct. You've performed the differentiation, but we can simplify it as well. Minus 3 times positive 4 is minus 12. All right. Now you can go straight from there to there. All right. The important thing is that if you just went like this, y equals, that's when it's wrong. Okay. You need to be really clear. Y, dy on dx. Okay. Here's the function. Here's the derivative. Make sure you've got the notation correct. That's one of the performance standards we assess. Okay, let's move on to C. We've got 4x squared plus 7x times x take 2. Now, let's check our process. Ensure all terms are expressed in the form x to the n. Yep, that's true. The function is fully expanded. It's not. Okay, we're going to need to perform FOIL here to fully expand it, and then we can differentiate it. All right, so this function, all I'm going to do is maintain equality as I expand it. Whenever I do expansion, I always encourage students to do it slowly, all right, rather than rushing it, because it's when you're doing those simple things that people tend to make mistakes that cost you sort of 1 mark. They're just annoying marks to lose. It's better to do it slowly and steadily and correctly than make a mistake and have to go back and rub it out, make a mistake and have to go back and rub it out, and it sort of panics you. So FOIL, we're going to have 4x to the 3, take 8x squared plus 7x squared, and then take 14x. Okay, that's what it expands to. Let's collect the like terms. We've got minus 8x squared plus 7 lots of x squared. Okay, if I have minus 8 plus 7, that's going to leave me with minus 1 lot of x squared. All right, we don't need to put the 1 out the front, the coefficient, because by itself it insinuates we've got 1 lot of it. All right, so everything's at the top, it's fully expanded, it's x to the n, we are ready to differentiate. So watch this, y equals, but now we're differentiating dy on dx. All right, very clear with the notation. Here's y, here's dy. So it's going to be 12x squared, take 2x, take 14. All right, so I did it all in one go there. All right, so I didn't write it out as a product. You don't need to do that, and you can jump straight to there. Y equals, very clearly, dy on dx. Okay, let's move on to D. E, we've got y equals x squared take 4x on top of x. All right, so we will learn some rules on how to differentiate this as a fraction in the future, but for now we're going to have to simplify it. because we need to express everything at the top of the fraction, and at the moment we've got this x at the bottom. What we're going to do is split the denominator. That's the process we're going to use here. So this is equal to, another way we could write it is like this. And of course that's true, right? Like if you have, let's think of one. 3 on 4. One way we could write that is 5 take 2 on top of 4. Alright, 3 on 4 is equal to 5 take 2 on top of 4, which could be written as 5 on 4 take 2 on 4. Okay, do you see how if we have this fraction, one way we could write it is like this, and of course another way we can write it is like that. We're just going backwards with fraction operations. All we're doing is making sure the denominator applies to both parts of the numerator. We can split the denominator, we can't just arbitrarily split the numerator. Okay? So let's proceed. Now we're going to simplify these. All right? And with both of them, we're just going to use rather than let's use the index laws. Okay? So what I've got here is I've got x to the power of 2, and what I've got at the bottom is x to the power of 1. And because they have the same base, I can use our first index law. The top power take away the bottom power. Alright, so that's what my first term is going to simplify to. And my second term, I've got x at the top, x at the bottom. You can just say they're going to cancel. They're a product at both. So that's going to simplify to 4. So we have x take 4. That's what it's simplified to, right? X to the power of 2 take 1. That's going to be x to the power of 1. Take away 4. We don't need to express it as x to the power of 1. So here's the function, here's the function, here's the function, here's the function. All of these things are different ways of expressing the same function. Now we can differentiate it. It's at the top, x to the power of n, fully expanded, bang. dy on dx equals derivative of kx is k. Here we have derivative of 1x. All right, the 1 is invisible, right? We just write x. Derivative of 1x is going to be 1. 4 is a constant, disappears. Okay, derivative of a constant is 0. So our derivative, our slope function is 1. Here's another way we can confirm that. What is this the equation of? What is it? If I was to say, what kind of function is that? It's the equation of a line, a straight line. What's the slope of this line? 1. If you were to draw that line, it's going to look like that. It has a slope of 1. What's the slope function? 1. Doesn't matter where you are on that function, the slope is always 1. Okay? So it's confirmed from our understanding of lines. It's confirmed from the calculus process that we've employed here. Okay, so that's D. Let's move on to E. And on E, the index laws are going to be a little bit more complex, but the same principle applies. Okay, so whenever we have, this is going to be a little side hack as well. Let's just focus on this part first, x root x at the bottom here. Whenever we have x root x, we're going to write that as x to the power of 3 on 2. And I'm just going to show you why that's true first. X is x to the power of 1. Square root of x is x to the power of half. And we're multiplying, right? X root x means x times the square root of x. So if we have x times x to the half, the same base, so we add the powers, 1 plus a half, and 1 plus a half is 3 on 2. So whenever you see x root x, x to the power of 3 on 2. Similarly, but you see it less common, x squared root x will be x to the 5 on 2. Okay, so definitely remember this one. This one might pop up, but it's more rare. Okay? So, our first thing is to express everything as x to the power of n, right? So this is still the same function. It's x to the half, and then over here I'm going to have x to the 3 on 2. Alright? But here, the x is at the bottom. We need it to be in the numerator. We need it to be at the top. So we use the negative index law. All right, everything's at the top of the fraction. Everything is expressed as x to the power of n. We're ready to differentiate. All right, so that's going to become, I'm going to write this one out a bit more slowly, half x to the minus half. N, x, n take 1. 1 take away half take away 1 is going to be minus half. All right, similarly, we've got 5. We bring that n out the front. Minus 3 on 2, x to the power of minus 3 on 2 take away 1, minus 5 on 2. All right, let's show you how we get that. Minus 3 on 2 take away 1. That's going to be minus 3 on 2 take away 2 on top of 2. That's going to be minus 5 on top of 2. Minus 3 take 2, minus 5, denominator stays as 2. Okay. Now, in your test, I've made an error here. It's a notation error. What did I forget? Very good, yeah. So when we've got y, we use dy on dx. When we have f of x, what do we use? F dash. Very good, okay? So make sure we're clear about that. Otherwise, we just have equals, equals, equals. This is not equal to that. We've done something. We've performed a process. We've differentiated. We've made it from the function to the derivative function. And now from there, we can simplify that a little bit. All right? And now I am going to simplify this one. And then I'll talk about where you're getting marks for it and so forth. So here we have 2 times a half. They're going to cancel, right? 2 times a half is 1. So that we get rid of that part. And x to the minus half, we could write as 1 on top of x to the half. All right, so they're the kind of things that I'm going to do. Here we have 5 times minus 3. That's going to be minus 15 on 2. I'll leave that one like that for now. Now we said x to the half is the square root of x. Here we've got a negative power again, so we'll take that to the bottom as well and make it positive. Okay, and when we have x to the 5 on 2, if we want to express it in terms of roots, what is it? X squared root x. Okay, so the reason I show you that is because the textbook tends to express their answers in this form. Where's the error? Negative. Oh yeah, cheers. Yeah. Good pick up. Negative 15, negative. All right. So when we express, we've answered it like that because that's how they tend to do it in the textbook. Now, in the test, on the first page, it's going to say, differentiate, there is no need to simplify. So you're going to get full marks here. All right, these questions probably worth 2 marks because of the algebra involved in simplifying it first. So algebra, 1 mark, differentiation, 2nd mark. You get full marks if you write that. But you are welcome to go on and write it like this. It will just take more time. Okay? The only time you are required to simplify, it's going to be very clear, and I'm going to point those out to you in coming weeks. Nonetheless, I need you to be competent at that kind of algebra and understanding. Okay, so in the test, most likely we're getting full marks here. There are certain examples where we do need to understand this algebra, so it is good to practice it at this stage. Okay, so full marks there, provided we're using the correct notation, right? F of x, and then we're differentiating. Okay, so that's simple differentiation. That's going to be enough to get started on the exercise. Let me talk about something on the front here. Okay, on the front we've got the checklist. All right, and I've written down all the questions there. And you can see with 2A, right, there's some extra questions, there's some supplementary questions that I'm encouraging you to have a go at that I haven't listed on the checklist. And 2B, I've got written there ESL, that's every second letter, so you just sort of do each second one. Now, sometimes this might not be feasible for you to do all of them. All right, it might be very difficult to get everything done. Okay, and that's okay. What I think is a better strategy is that you understand the concept, okay? It's not about doing the work, it's about understanding the concept. And so if you've grasped If you've got a skill, if you understand it, if you've grasped it in your mind, there's no point doing questions over and over and over and over again about it, okay? That's just going to be boring and monotonous. What you need to do is make sure you're challenging yourselves. And the textbook's generally set up in such a way that the later questions are the harder ones, isn't it? And it's good like that. So if we're finding a skill easy, if we're finding question 1 easy, jump and do the last 3 or the last 2. And then if you find the next question easy, same thing, right? You don't need to do every single one. You need to be constantly challenged, okay? Constantly challenging yourself and asking yourself, do I understand this concept, all right? It's not about the workload. It's not about ticking all the boxes. It's about grasping the concepts. That's the purpose of the textbook. And then again, I've written every second letter for question 1, but if you think it's a skill you need practice with, that's when it's time to do every one. Do every single one of them. Make sure you've got it completely. All right? If you need more resources for anything, let me know. I'll help you out. But for today's lesson, let's work on 2B, and I'll come around and see how we're all doing with the first principles.